couple days ago, last time we met, about some basic transformations. Okay, we named them. I'm wondering if you remember what those names are. Put your hand in the air if you think you're a player. Can you name one of those basic transformations there, Paul? Okay, so horizontal is a direction. It would be a sort of way of describing one of those basic. Rigid is a way of generally describing, once more. I'm kind of looking for like a specific thing that we do to a graph. Jack, is your hand in the air? Oh, a reflection. Very good. A reflection, also known as a flip, is where we perhaps would multiply either a function or the argument of a function by a what? By a negative. That boy, Alex, by a negative. So in other words, if we see a negative on the inside, it's going to be a horizontal flip. If we see a negative on the outside, it's going to be a vertical flip. And if we see both a negative on the inside and a negative on the outside, then it is a horizontal and vertical flip. Okay. And we actually had, here on my screen, I'll slide it up to it. We actually had some pretty solid examples. Yeah, there we go. Of such transformations. The square root function being a great illustration of what we're talking about there, right? So when we discuss flips, thank you very much, Jack, that's one of the two types of rigid transformations that we've discussed. Rigid meaning where the shape is maintained. Perhaps we just change its orientation in this case. Or we change its location, right? I use a little analogy of the black chair. So Luke, tell us what kind of other rigid transformation we studied. A shift or a translation. Those two interchanged synonymously. And a shift or a translation, we said, was where you're adding or subtracting something either to the inside of the function or to the outside of the function, right? If you add it to the inside, it's horizontal, but it's backwards. It's the opposite of what you would think. You would think a plus would move it to the right, and yet a plus moves it to the left. When you do an operation on the inside, it's counterintuitive. It's the opposite of what you think. We saw when you add or subtract something from the outside, it is what it is. Subtraction moves it down, addition moves it up. Okay, so those were our examples of rigid transformations. Today, you guys are going to look with me at some non-rigid transformations. Okay, so in your notes, you can say, all right, we're going to look at some non-rigid transformations. All right. Now, I can't use my little chair example now because I'm not the Incredible Hulk. I can't take that chair and squeeze it down into a tiny chair or stretch it out to a huge chair. But I do have the power of one note. And so I'm going to demonstrate what I'm talking about here. So like, let's just say, that's a crappy circle. Let's just say, that's better, that I've got a circle right here. Okay. A non-rigid transformation would be if I take that circle and I don't change its position necessarily, but I change its proportion. I change its size. In other words, it's still this circle shape, it's just smaller or bigger, right? See what's happening there? So the way that we would describe a non-rigid transformation is if we are going to stretch or shrink. Okay, stretch or shrink. Sometimes the word shrink is replaced with compress. I've seen it written compression, right? You guys ever wear compression shorts? You athletes, y'all know what compression shorts do? You keep all your man parts where they're supposed to be when you're out running around on a field. Some compression shorts have like a built-in girdle. You guys ever worn a girdle before? Jack's nodding his head. He's like, oh, I got a strong girdle game, Coach Morgan. What do you wear a girdle for, Jack? Attaboy, that's right. You wear a girdle to keep your hip pads and your butt pad in place when you're playing football, oftentimes. And like when I played baseball, back before I came a PO, which is a pitcher only, when I played the field and hit, I would wear compression shorts, and they had like a little pad on the hip for what? Yeah, sliding shorts. We call them sliding shorts, but they were compression shorts, right? In other words, compression shorts are like, they're tight, they're form-fitting, They keep stuff where it's supposed to be, whether it's pads or private parts. Okay, so the idea of compression is that okay, we're going to take a shape and we're going to shrink it down. All right, the way that we stretch or shrink is by multiplying, not by a negative, but by multiplying by a scale factor. Okay, you multiply by a scale factor. Okay, now what do I mean by scale factor? I'm going to get a little illustrative prop over here. Anybody ever seen a ruler that looks like this? Has ever seen a ruler? Right, this is a ruler much like what my dad uses. My dad works with blueprints a lot, right? He's in HVAC, heating, ventilation, and air conditioning, and he works with blueprints. Okay, so like let's say he's not, but let's pretend like he's gonna install the HVAC system here at the new field house that CBHS is building, right? So when they get, in other words, when they get ready to put in the heating and ventilation and air conditioning systems, let's say he's going to take the blueprints of the school, or of at least of that footprint of that physical building, and he's going to plop it down on his desk. He's got a desk that's slanted so he can sit and do his blueprints on it. Are those blueprints going to be actually the same size as that building's footprint over there? Of course not. That'd be ridiculous. Nobody works that way. What do? They scale it down. To scale means that the building's shape is maintained, it's just shrunk down by a particular factor. Okay, hence an engineering ruler like this, which you guys would use if y'all ever went into that kind of field, right? You might notice that, let's see if I can find it. This side right here that I'm facing towards you is a normal 12-inch ruler. Okay, so like if I wanted to measure from here to here, that's 5 inches. Okay, from 5 to 10, that's 5 inches. Okay, but if I wanted to, quote, scale that down, then I could flip this ruler to a different scale factor. All right, so like on this one, I flipped it over, and this is 15 inches. So what scale factor did I use? It started out, it was 5, now it's 15. Of what number? 3. I used a scale factor of 3. So you might see at the top of this ruler where it says 3, that's a scale factor, to where 5 inches is this length right here on my blackboard is actually 15, quote, inches. Okay, and it goes up. There's 6 different scale factors on this particular ruler. So the idea is that I can take something, let's say y'all are comfortable dealing with the square root function, so let's deal with that. Let's say I could take my normal function, y equals the square root of x. Okay, we've discussed this is a basic parent function. We know what its graph looks like. 1, 1, 4, 2, and heck, we'll go on all the way up to 9. 7, 8, 9, 3, all right, pretty decent looking little graph right there. So that's our normal function, okay? Watch what happens when I decide to multiply a scale factor. And I'll pick a simple scale factor of 2, okay? What do you think is going to happen to that curve now? What happens if I multiply, let's say in orange, I want to look at y equals 2 times the square root of x. A scale factor of 2. What is that going to do to the shape? What do you think? You can guess and be wrong, and that's totally fine. Nobody's going to yell at you. James. It is going to make it bigger, right? It's going to make it bigger in the vertical direction. Because watch now what happens. You see those outputs over there on the green one, right? When I plug in 0 over here, I get out 0. What do I get when I plug in 0 over here? Square root of 0 is 0. 0 times 2 is 0. I still get out 0. So that starting point doesn't change, right? This isn't a change of position. It's not a shift or translation. It's a change of size. So like when I plug in 1 over here in the green, when I get an output of 1, and yet look what happens. What do I get when I plug in 1 over here on the orange one? What's the square root of 1 times 2 I get an output that's doubled. Okay, what happens if I plug in 4 over here? In green, I plugged in 4 and I got out 2 because the square root of 4 is 2. In orange, I plug in 4. What's the square root of 4? And then times that scale factor that's out front. 2 times 2 is 4. So I've now doubled. And then, you know, we could go all the way out to 9. What am I going to get out when I plug in 9? Square root of 9 is 3. 3 times 2 is 6. Oops. So it's still the same kind of curve. It's just taller. If I were to superimpose, whoops. If I were to superimpose this green one, gosh dog it. We'll try one more time. There we go. Now we're cooking. If I were to superimpose this green one, I think I did a decent enough job of making my tick marks match. Yeah, that doesn't look too bad. Right? If I were to superimpose the green one and the orange one together, then you can see the orange one. How would you describe it? Use simple words. It's higher up. It's taller. It's bigger, right? By a factor of 2. So one would think that if I wanted to maybe, let's say, get a little wild and crazy here, we'll do a red one and say y equals 3 times the square root of x. What would you think would happen then? It would get even bigger. And 4 would make it bigger. 5 would make it bigger. 6 would make it bigger. So in other words, the bigger the scale factor out front, the taller, or the more that that's stretched, that curve is stretched in the vertical direction. Generally speaking, and again, we've used a couple of specific examples here with the square root function, but let's generalize it. Generally speaking, if we say k times a function, where k is my scale factor, right? K constant, right? Alliteration there, k constant. So if I multiply k, some number, by my function on the outside, like we did 2 times the square root, or 3 times the square root, or 4 times the square root, whatever, right? Depending on the size of that k, our curve is either going to be stretched or shrunk. Now, we have talked about stretching. We have not talked about shrinking. So what do you think I could do to shrink my graph? Jake. Louder. Okay, so not a negative number, because we know a negative will flip it, and then that's a whole nother ball of wax. I hadn't heard from Tiago yet. Tiago. Very good. Let's multiply by a number between 0 and 1. All right. So like, for example, let's see here. In orange, we had y equals 2 square root of x. In green, we had y equals the square root of x. Why don't we do, in black, we'll do y equals 1/2 square root of x. Okay. And I know this is going to kind of be weird, so let me get rid of my axes here, and we'll just work on the one axis. Okay, and I know I've got multiple tick marks, but you guys can sort of ignore those green ones. All right, so like if I wanted to just use the orange axes right here, right? What would, like if I plug in 0, what am I still going to get out? 0, because the square root of 0 is 0, 0 times 1/2 is still 0. So on my little black graph there. But look, what if I plugged in 1? What's the square root of 1 times 1/2? 1/2. What if I plugged in 4? The square root of 4 times 1/2 is only 1. What if I plugged in 9? What's the square root of 9 times 1/2? 1.5. Right? So you see this one has been compressed vertically. It's like somebody put a big heavy book on the top of it and just kind of squashed it down there. Okay? So these are 3 examples. We got our parent function in green. We got the stretched vertically function in the vertically stretched function in orange, and we got the vertically compressed function in black, right? And it depends on the size of k. So let's generalize this, like I said. Okay, if k is greater than 1, then you've got a vertical stretch. and again, I use stretch in quotes. Actually, I'm blanking on the formal name that they use for it. I don't think it's expansion. That's not the right name. There's some fancy name like compression, just in the opposite direction. But I call it a vertical stretch. All right, so and then we said if K is between 0 and 1, then we've got a vertical compression or shrink. We got some shrinkage going on there. Okay. Now, to Jake's point, what if there's a negative? Okay. That's where we need to sort of split it up and consider, okay, the negative is going to be a reflection, a vertical flip. And then if it's like -5, then we would consider, okay, what is this 5? This 5 would be my stretch or my compression, and in that case, it'd be a stretch, right? So you would have actually 2 transformations going on there. We'll look at an example like that in a minute, okay? But any questions on how this is our first non-rigid transformation? Any questions on how this kind of comes about? What this looks like, why it looks like the way that it does? All right, let me show you a little website. Because one of the greatest tools that you guys have when you're talking, and by the way, it's an Algebra 2 lesson. Normally, you don't kind of see this stuff in Algebra 1 that much. But when you get into Algebra 2 and you guys start dealing with transformations, one of the best tools you're going to have is this. You know what this is? A graphing calculator. Right? It's got a big old screen on it. Some of y'all's older siblings might have one of these. And when you're, in Algebra 2, you start learning how to use a graphing calculator. Well, you also have access to the internet, and the internet is full of free online graphing calculators. One of the best ones is at a place called Desmos, desmos.com/calculator. Okay. And what I tell my students is, hey, if you really want to see what effect a constant out front, for example, has to do with the shape of a function, just start graphing stuff out. Like we used the square root example already. So I'm going to use a little bit of a different example. We'll say y equals the sine of x. All right. This is a trigonometric wave function. You guys will study about that in trigonometry. That's a pretty cool looking curve. All right. Now, all of a sudden, I'm going to start making a second curve, y equals 2 sine of x. And what do you notice between the red curve and the blue curve? It's so obvious. What happened? It was stretched vertically. And all I have to do is just change that little parameter. And you see that, oh man, he's making it go bigger. And what's happening to the amplitude of that wave is that wave is getting taller, right? I'm changing the amplitude, which is a characteristic of a wave function. Okay, but what if I wanted to make it like 0.5? Oh, now what happened? It got smaller, or 0.1. Ooh, it got tiny. What if I just make it 1? It's the same graph, okay? What if I make it 0? It flattened that curve out to a straight line, because y equals 0 is the equation of a horizontal line at the x-axis. So that's why we're parameters on there. If you go back to the notes and you look at those parameters, that's why we were focusing in on the fact that k greater than 1 is a vertical stretch. K between 0 and 1 is a vertical shrink. And then, okay, well, what happens if it equals 1, right? Well, there's no change at all. What happens if it equals 0? Okay, well, it's a flat line. It's nothing. It's just y equals 0. And then to Jake's point, again, what if I make it a negative value? Okay, let me find my cursor here. All right, so like if I wanted to make it, let's say a -2. Can you see what has happened now? It has flipped and stretched. So you would only want to consider one at a time, right? You would only want to consider maybe the negative, just the flip. And you would only want to consider the 2, the stretch, and then when you put both of them together, a stretch and a flip, that's what you get, okay? And do you see how easy it is to play around with the graphing of this, right? That's where you sort of figure out what happens. What do I do? There's a really neat activity. I can't do it with you guys because y'all don't have a computer right in front of you. But there's a really neat activity that I'm going to try to work with my freshmen tomorrow. It's sort of a fun wrap up to the third quarter, and it's like I'll kind of show you what it's like. Let me see if I can get to it rather rapidly. Desmos activity, marble slide. Marble slides. I think this should take me to it. Yeah, give me just a moment. My computer's being slow today. Come on, baby. Now we're cooking. Marble slides lines. No, I don't want marble slides lines. I want marble slides parabolas. I think this will be it. Keep your fingers crossed. It's a little game that you get to play on the internet by transforming a particular function, and you just kind of get your hands dirty. And you guys, I'll do one with you. Y'all can be some guinea pigs if it works out. Because the idea is you got a parabola. You guys remember what the shape of a parabola looks like, right? All right, so you got a parabola, and you got some little stars that are on the graph, and you hit a button, and like some little purple balls fall onto the parabola, and the is to get the. Let's see if I can turn it on here. The goal is to get the balls to hit the stars. All right, how do I do this? How do I do this? Let's see here. Y'all sit tight. Give me just 2 minutes. Let's see here. I want that. Can I do student preview? Yeah, let's try that. All right, sweet. Okay, so obviously there's no need for a parabola right there. I'm just going to hit the launch button, and then the purple balls are going to fall and hit all the stars. I'm projecting wirelessly right now, so it's not coming through very smoothly from y'all's perspective, but here's a different one. All right, so like there's a parabola whose equation is drawn out over here, right? And what I need to do is I need to transform that parabola so that when I hit my little launch button, the purple balls all roll and hit the stars. Like, for example, if I hit launch right now, am I going to get all the stars? No, of course not. Here, watch. Fail. Okay, so sadly I failed. So what could I do to that blue parabola to make it happen? What do you think, Jack? All right, what would that do? So let's think about what that would do. Before I let the cat out of the bag, Jack's suggestion was change the 8 to a 0. So that plus 8, what kind of transformation is that? We talked about it on Tuesday. It's a shift in which, Paul Cover, in which direction? Good, it's a vertical shift. So if I eliminate that plus 8, all of a sudden, my parabola is back there. Now, do you guys think I'll hit all the stars that way? No, so let's put our plus 8 back in. Jack, that's not a bad guess at all. Plus 8. Okay, so I've got my parabola located a little bit higher. Candy Autumn? Ooh, and how do I flip it? James? I'm going to multiply by negative on the outside. Very good. And watch what happens. Boom! It's flipped, and now if I launch it, all my purple little balls bounce down the hill, and yippee skippy, I've got all the stars. Success! All right, so like you're in a game like this, you're just sort of playing around with it. That's what I'm trying to tell you, is that like with a graphing calculator, which this is a Desmos activity, so they're using their calculator, you guys can play around with, you can get your hands dirty, so to speak, and see, what happens when I alter this shape by multiplying by a negative on the outside? You know, what happens if, let's see here, I think this last one will be it, because this one's where you get a little bit tougher. Okay, so like what happens if, and again, this might be going a little bit beyond what you guys are doing, but if you wanted to restrict to only part of the graph, like they said x is less than 5, that's why the parabola got cut off right there, right? So like if I were to, first of all, I kind of need to slide it to the left, don't I? right? Wouldn't that be nice? How do I go about sliding it to the left? What type of translation is that? Is that horizontal and therefore on the inside and counterintuitive? Or is it vertical and therefore on the outside and it is what it is? We want it to be horizontal. So if I want it to slide to the left, I must do what? It's counterintuitive. I gotta add. I gotta add on the inside. So let's add something. Let's I don't know, let's add 4. Let's see how that goes. Ooh, now it slid it over to the left. Now that's obviously not going to get it done, right? So maybe if I slide it back over to the right, maybe if I put my vertex right here, would that be good? Let's try. So how do I slide it to the right? Subtract 4. But because I've got this sort of parameter right here, maybe I don't want that. So let's see if I can take that out. All of a sudden now, I've got the whole parabola, okay? I want you to ignore this little star because, again, I think this goes beyond the scope of what I've taught you guys. But kind of playing around with this, what do I need to do to the parabola now? Describe with words. I've already heard from Jack. Somebody else that hadn't spoken up just yet. Describe what would you want me to do to the parabola so that I can hit both of those, again, ignoring this bottom right-hand star, but I can hit both of these stars. Let's see here. Andrew, I hadn't heard from you yet.
Expand it.
Okay, so expand it. In which direction? The up-down direction or the left-right direction? Left-right direction. Now, how do I go about doing that? Okay, go back to my notes here. And these two were vertical transformations. These were 2 vertical stretches and shrinks. So what do you think I could do to horizontally affect something, Alex? So like the K being multiplied on the outside affects it vertically. Let's put the K on the inside, right? So your next bullet point here, as you guys are taking notes, your next bullet point will be if I wanted f of K times X, okay? So this is, when we have it on the outside, that affects it vertically. All right? But when I have it on the inside, come on, OneNote, wake up for me. When I have it on the inside, it's going to be a horizontal effect. We are horizontally. Now, you guys remember how I said when you do something on the inside, it's backwards, it's counterintuitive? So if I want to make it bigger, I should multiply by a what? By a small number. Not negative. Negative flipping. That's what we don't want to put two transformations all together in one. So check this out. If K is bigger than 1, it's going to be a horizontal shrink. It's backwards. It's the opposite of what you would think it would be. And if K is less than 1, let's say between 0 and 1, pardon me, then we're going to have a horizontal stretch. In other words, as Andrew phrased it. Andrew, how'd you phrase it with our parabola on the star thing? You said you wanted to expand it. There you go. I like that. So like if we wanted to expand it, and we'll wrap up with this, we'll kind of finish this up. Like what would you want me to multiply by on the inside to expand it? 1/2. Oh, fabulous. Let's try that. Okay, so 0.5. Now all of a sudden, something shifted. Why did it shift? Well, that's kind of an Algebra 2 question. Sorry. I'll go ahead and answer my own Algebra 2 question. You guys haven't had Algebra 2 yet. The reason that it shifted is because the 0.5 needs to be applied to the whole argument, not just the x, to the whole argument. All right, question, James? Brother, I was hoping you'd say that. Do you remember the syntax? It was like the little, not brackets. You know, do x is less than 5. Oops. Brackets there. And then I don't think I need a semicolon. There we go. All right, so x is less than 5. You want to try that? Fingers crossed. Oh, we overshot it. So with this, and obviously we're kind of out of time for today, but with this, what your mind should be doing right now is you should be thinking, how else could I transform this? Maybe make it a little taller, right? Maybe make, instead of a 2, maybe make it like a 3, and shove it over like a little bit, maybe instead of a 4, maybe like a 3.8, something like that, to where it, instead of having such a wide curve and throwing it out farther, maybe we have a, see, I even missed it there. Look at that. Anyway, I want you guys to play around with graphing calculators between now and when you take Algebra 2, so that you can kind of visualize more about some transformations, all right? Hey, we'll have our last class of the quarter tomorrow, and I look forward to seeing you guys then. Live Jesus in our hearts. All right, y'all skedaddle on out here. Thanks again, fellas.